Precalculus, lesson 12.9, mathematical induction. Now, if you're wondering about lesson 8, um, so big topic of this chapter, sequences and series, and a type of sequence would be iterations. That would be where you have some function and some initial value. We'll call that x sub 0. You plug x sub 0 into the function, and what it solves to be is your first iterate x sub 1, and then x sub 1 you plug back into the function, and what it solves to be is x sub 2, your second iterate, etc. And that's something that we've done a couple times already this year. So, for the sake of brevity, we are skipping lesson 8, and I won't bother putting anything like that on the test for this chapter. So, yep, that's lesson 8. So we're in lesson 9, mathematical induction. So here we go. So this is 12.9, mathematical induction. It's basically a type of proof, or if nothing else, oftentimes mathematical induction is one step in larger proofs sometimes that takes kind of a base case and it shows that some property or relationship is true for all cases. And it can be likened sometimes to setting up dominoes, where basically you say the first domino falls over, and then you show that if any domino falls over, then the next domino will also fall over. And if you show that if any domino falls over, then the next one will fall over, and you have already shown that a domino fell over, then you are proving that all of the dominoes will fall over, that it will keep going domino after domino after domino after domino forever, because if the fifth domino falls over, then the sixth one will. Oh, but if the sixth one fell over, then the seventh one will, because if any domino falls over, then the next one will also fall over. Or sometimes it's likened to rungs of a ladder, where you show that the ladder does have a first rung. Then you also show that if the ladder has any rung, then it also has a next rung. Therefore, the ladder keeps going forever. Okay, so that's kind of what's going on. And basically, it has three steps to it. There's the base case, also sometimes called the basis. And then there is the inductive step, or sometimes called the inductive hypothesis. And then the conclusion. And the base case, what you're doing there is you're showing that relation works. I'll say that I'll just leave it as show that's true for n equals 1. And then the inductive hypothesis kind of has two parts to it. Assume true for n equals k. And then what we do is we show true for n equals k plus 1. The n equals k is basically saying this is true for a domino. Then the showing that is true for n equals k plus 1 is the next domino after domino k. So if it's true for k and also true for k plus 1, then it must be true for all. All right? So there are kind of two flavors of this kind of proof that we have in this lesson. And so what we're going to do is we're going to step through an example and then see in more detail how it works with that. All right? So here's one example. It'd be like this. Show that 1 plus 5 plus 9, 1 plus 5 plus 9 plus ... plus, and the relationship going on here, the nth term is 4n minus 3 plus 4n minus 3 equals n times 2n minus 1 for all n. In other words, we want to show that the sum of the first n terms, where the nth term is 4n minus 3. In other words, if you wanted the sum of the first 12 terms, it would be 1 plus 5 plus 9 plus ... plus 4 times 12 minus 3. Would that be 45 would be the last term, equals 12 times 2 times 12 minus 1. And we want to show, though, that this will work regardless of how high we go. That'll work for any number of terms. Okay? All right. So, step 1, our base case. We just want to show, so we'll say show true for n equals 1. And when you do these, please go ahead and give a little description or explanation of what it is that you're doing. This is good mathematical practice to give a little bit of commentary on what you're doing. All right, so what is our first term? Our first term is 1. Or rather, if we're using the representation of it there, our first term is 4 times 1 minus 3. And we want to show that equals 1 times 2 times 1 minus 1. All right, well, this is 4 minus 3. 4 minus 3 is 1. Cool, that does match what our first term was there. Equals 1 times, well, 2 minus 1 is 1, and so we get 1 equals 1. All right, so it is true for n equals 1. Now what we're going to do is we're going to assume true for n equals k. And here we just take what we originally started with, and instead of using n, we use k. In other words, we're saying 1 plus 5 plus 9 plus ... plus 4k minus 3 equals k times 2k minus 1. Now we could, it's just unnecessary for the type of proof that we're doing. We could do, okay, well, let's show it's true for the first term, and let's show it's true for the second term, and let's show it's true for the third term, and then let's use k. But it's not necessary for what we are doing here. Okay, so we assume true for n equals k. In other words, this is our arbitrary rung of the ladder, or our arbitrary domino. And now we want to show that it's true for the next rung or next domino. And so then what we do next is we say show true for n equals k plus 1. So what I'm going to do here is I'm going to have 1 plus 5 plus 9 plus ... plus 4k minus 3 plus whatever the next term in this sequence would be. Now, there are two ways that you can do it. One way is you can take this term here and you can plug in k plus 1 for k. Okay? So that would give you 4 times k plus 1 minus 3. The other way that you can do it is you can just look at what's happening with the pattern. What's happening with the pattern is we're going up 4 at a time, right? Plus 4, and then our next term is 4 greater than that. So our next term here would be 4 greater than that. So instead of 4k minus 3, we're going to get plus 4k plus 1, because that's 4 greater. Okay? You would get the same thing if you plugged in if you did 4 times k plus 1 minus 3. Because this would become 4k plus 4 minus 3, and that would give you that 4k plus 1. Okay? All right, so equals, now we're showing this is true for n equals k plus 1. So we're going to take our original expression here, and instead of n, we're going to plug in k plus 1, because that is the next term in the sequence. If you can get whatever term by plugging in a value for n, then the next term would be plugging in a value for, or plugging in n plus 1. Okay, so this is going to be, instead of n, we're going to have k plus 1 times 2n, or times 2 times k plus 1 minus 1. Okay? So I want to show that my left-hand side of the equation equals the right-hand side of the equation. That's what I want to show. Well, let's see what we can do. Well, I already have this equation here that I have shown to be true. In particular, I've shown that all of this equals that, right? So I can take all of this, right? 1 plus 5 plus 9 plus dot 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 plus 4k minus 3, and I can substitute that with k times 2k minus 1. I know that's a true statement. And I have that plus 4k plus 1. And I'm wanting to show that that does equal my expression, my original expression here, with the k plus 1 plugged in for n. So that does equal k plus 1 times, I guess I can do a little bit of simplifying here, times 2k plus 2 minus 1, but that gives me times 2k plus 1. Okay, so at this point, we just need to work independently with the left-hand side of the equation and with the right-hand side of the equation. In other words, we can't like do any moving from one side to the other, because we're kind of pretending like this is we don't know for sure that this is true, and we want to show that it's true by simplifying or rearranging each side by itself, not doing anything from one side to the other. So I would just start out simplifying the left-hand side. So I have k times 2k, so that gives me 2k squared, right? And then minus k, and I have a plus 4k plus 1, and let's see what that simplifies to. So I still have my 2k squared, total of plus 3k plus 1, right? And let's see what that equals. When I FOIL this, I get 2k squared plus k plus 2k plus 1, and that is 2k squared plus a total of 3k plus 1. And notice the left-hand side equals the right-hand side that I have there. All right? So at this point, we just need to kind of do a nice little conclusion, just a concluding statement. And so we can say something like this. Since the formula for n equals k is also valid for n equals k plus 1, the formula must be true for all n. And I'm going to do a little box here to say I'm done with my proof. So that's that flavor. You can, double check the notes and whatchamacallit, and review, go back and review some of the steps as needed. So there's one other type of this, and it would look like this. We're going to do show that 7 to the nth plus 5 is divisible by 6. All right, so we want to show that 7 to any power plus 5 will always be divisible by 6. And the overall steps are the same, just how we carry them out looks a little bit different. So step 1, base case. base case. We want to show that 7 to the first plus 5 is divisible by 6. Well, 7 to the first plus 5 equals 12, right? Equals 12, and 12 equals 6 times 2. And how do you show that something is divisible by 6? You can factor a 6 out and be left with 6 times an integer. Okay? All right, so the base case works. Next, step 2. The inductive step, let's say show true or assume true. Assume true for n equals k. And what this would look like is it would look like 7 to the k plus 5 equals 6. I'm just going to go with an r here. 6r, where r is an integer, right? Because if 7 to the k plus 5 equals 6 times some integer, then 7 to the k plus 5 is divisible by 6. Okay, next we want to show true for n equals k plus 1. And now here's where it looks a little bit different, because we're not adding a next term like we did up in the previous example, right? The previous example, here, I added the next term to create the next step, to create the next value. But I'm not adding a term now to create the next value. What am I doing? I am multiplying by, well, instead of 7 to the k, I want to get to 7 to the k plus 5, right? I'm sorry, I want to get to 7 to the k plus 1. So instead of 7 to the k, I want this to end up looking like 7 to the k plus 1 plus 5 is what I want to get to. Okay? So I want to show that that equals 6t, where t is an integer. That's what I want to get to. But I want to get there starting with this right here, starting with this. So I'm going to go my 7k plus 5 equals 6r. And I'm going to subtract 5 from both sides. And you'll see why in just a second. 7k plus, I'm subtracting 5 from both sides. So 7k equals 6r minus 5. Now to create 7 to the k plus 1, I can multiply both sides by 7. So I'm going to say 7 times 7 to the k equals 7 times 6r minus 5. So what does that create on my left-hand side? Well, 7 to some power times 7 again raises the power by 1. So this gives us our 7 to the k plus 1 equals, and what do we get here? 42r minus 35, right? 42r minus 35. Okay, but my goal is to get to 7 to the k plus 1 plus 5. So I need to add 5 to both sides. So that'll give me 7 to the k plus 1 plus 5 equals 42r minus 30. Now my goal again is to get 7 to the k plus 1 plus 5 equals 6 times some integer. Well, so then can I factor a 6 out of the right-hand side? 7 to the k plus 1 plus 5 equals 6 times 7r minus 5. Now if r was an integer, then 7 times r minus 5 will also be an integer. So we have shown that the k plus 1 term is still divisible by 6, because 6 times some integer You know, that is showing that it's divisible by 6. So we can jump into our conclusion then. So since the formula, let's just see, I'll do this. Since 7 to the nth plus 5 is true for n equals k and for n equals k plus 1. I'm sorry, since is true. That's too vague. I meant is divisible by 6. Is divisible by 6 for n equals k and for n equals k plus 1. Then 7 to the nth plus 5 must be divisible by 6. For all n. Little box to say I'm done with my proof. And that is this lesson. So I have, I think, probably 2 of this first type that we did today, and then 1 of the second type for you for homework. And then 1 word problem that is also kind of based on this first type. Kind of a word problem. And yeah, let me know if you have any questions. But otherwise, if you can follow the format that I have and just kind of get a sense for what's going on, then that will do it for this lesson. Thanks. Bye.